Okay, so let's say that you're just chewing up some fat left and right all day long, and you're making a boatload of what? Acetyl-CoA. And if you're trying to get energy, what are you going to shuttle that into? Citric acid cycle. What is it, the first thing that acetyl-CoA combines with to form citrate? Oxaloacetate. So now let's say you're just chewing up fatty acids like there's no tomorrow. So you might get so much acetyl-CoA that you don't have enough oxaloacetate to keep up. And so you get this buildup of acetyl-CoA. And if that's the case, so that acetyl-CoA might start resulting in ketosis, sometimes called acid ketosis. You usually get a pH drop like that. So ketosis happens when you get this buildup of acetyl-CoA. And you just don't have enough oxaloacetate to keep up. This can happen during periods of, say, fasting, or it can happen from a high-fat, low-carbohydrate diet, as has become really popular in recent years, things of this sort. Cool. The idea is that we're going to form what are called, what's the magic word here? Ketone bodies. These are your three ketone bodies. They're acetoacetate, acetone, and beta-hydroxybutyrate. Those are your ketone bodies. So if you're cutting the carbs out of your diet, you might be really having a lot of fat in your diet at that point, so at least relative to the amount of carbs that are in your diet. So you're making a lot of acetyl-CoA. You don't have a lot of oxaloacetate to keep up. You might start making some ketone bodies. When else might this be occurring? Diabetes. So diabetes problem, they might have enough carbohydrates in their diet, they just can't absorb them. So with a lack of insulin, or at least functioning insulin. So in this case, they're still taking in fat, but they're not getting any carbs actually absorbed, even if they're eating them. And so they might have the same result. Lots of acetyl-CoA from beta oxidation and not a lot of oxaloacetate to keep up. First thing that happens, two acetyl-CoAs, 2 carbons each, combine to acetoacetyl-CoA. So you'll shuttle another one in, notice 2 more carbons, and that's where you get HMG-CoA. 6 carbons in total. Cool, one of your acetyl-CoAs pops right back off, and you get acetoacetate. So an acetoacetate can either be decarboxylated to form acetone, and it's in equilibrium with beta-hydroxybutyrate. So I would say these 3 lovely ketone bodies, those structures are probably worth knowing. So the reaction itself, I would probably know the process. So as far as knowing the structure, I would be able to recognize the structure of HMG-CoA. It's not the hugest thing in the world, might not be the worst one to know either. But yeah, probably not the worst process. Small carbon chains. When we start getting to big carbon chains, those are the ones that are hard to expect you to memorize. But this one's probably not so bad. Probably worth your time, sorry. So ketone bodies. So buildup of acetyl-CoA, we made ketone bodies. What's special about these?
Your brain can use them.
What's that?
Your brain can use them.
Your brain can use them. When?
Under starvation.
Oh, good. Your brain can't always use them. Only after several days of starvation does your brain say, you know what, maybe we should use something for fuel. So, because obviously you're starving for a reason, and in starving for a reason, maybe you need some brain power to figure your way out of this. Who can use them all the time? Heart. Your heart can use acetoacetate all the time. In fact, what surrounds your heart? Actually, there's fatty tissue surrounding your heart. So some people who go through various forms of anorexia and stuff like that often cut all fat out of their diet, and one of the things that can happen to them is they can get to so low in body fat, so to speak, that they even start losing the body fat around their heart, which is really a dangerous situation. So you want to have some fat around your heart because your heart relies on fat for its fuel. So in this case, it's got ready access just right around it, fatty tissue. Cool. So heart can use it all the time, brain only after several days of starvation. So in fact, that is the preferred fuel for your heart. What's the preferred fuel for your brain? Glucose. Sweet. Anybody know anybody with diabetes? Anybody ever actually smell the acetone on their breath? Yeah, me neither, because right now, these days, in this country, it's so regulated that people are always taking what? insulin shots and stuff like that, that it's usually not an issue. But back in the day, it was. So speaking of, interesting side note that has nothing to do with your exam, how did they test for diabetes back in the day? Doctor would taste their urine. I know. And they would taste to see if it's a little bit sweet. That's right. Just interesting tidbit. Aren't you glad you're not a doctor in the 1800s? All right. A little more demanding on you back then. All right. So now we've talked about the catabolism of fatty acids. Now we've got to talk about the anabolism of fatty acids. All right, so fatty acid synthesis. So when might you need to make some fatty acids? Because you know what? Most of us don't need to make any fatty acids. We get plenty of them. My grandma got plenty of them on her toast every day, right? So it's not the normal situation, but when might you need to make some fatty acids? So haven't eaten for a while, or you got a high carb, low fat diet, other way around. So then you might need a little more fat than you're taking in your diet. So you might need to make some. So in this case, we're going to take a boatload of acetyl-CoAs. So, and it kind of looks like, in at least the general overall reaction, looks like kind of the opposite of beta oxidation. Instead of taking a long-chain fatty acid and chopping it up into a bunch of acetyl-CoAs, we're going to take now a bunch of acetyl-CoAs and build them up into a long-chain fatty acid. So now it is definitely not the exact reverse of beta oxidation, a little more complex than that. So, but the overall reaction kind of looks similar. So in this case, where might you get a bunch of acetyl-CoA to make fatty acids from? Probably from glycolysis. So make a bunch of pyruvate, decarboxylate it with pyruvate dehydrogenase, make a bunch of acetyl-CoA that way. So, and again, this might be in response to a high-carb, low-fat diet, so you probably can do a whole bunch of glycolysis in such a situation. So one thing to note, so is this takes place in the cytosol. So got a problem, because where do you make acetyl-CoA? In the mitochondria. So if we're going to make acetyl-CoA in the mitochondria, but then I want to make some fatty acids, I got to shuttle my acetyl-CoA out of the mitochondria. So, and in this case, we have another shuttle pathway. Isn't this fun? So in this case, acetyl-CoA can't leave the mitochondria all by itself. So what we do is acetyl-CoA is 2 carbons. We combine it with oxaloacetate and make citrate. Oh, where have we seen that before? That's the first step of the citric acid cycle. In this case, though, instead of completing the cycle, the citrate leaves the mitochondria and goes out into the cytosol. That citrate is then reconverted back into oxaloacetate, releasing the acetyl-CoA. It costs energy to do this, though. So, and then the oxaloacetate will be converted into malate, so which requires the oxidation of NADH. So, and that malate can go back in the mitochondria if it wants to, or have a number of different fates. But the goal is that we turn the acetyl-CoA into citrate, because that can leave the mitochondria. Then we'll get the acetyl-CoA right back out. Okay, so our acetyl-CoA, turns out that's not actually what we're going to use as our substrate feeding into fatty acid biosynthesis. It's the initial substrate, I shouldn't say that, but when we actually start making the fatty acids, it's not it. So we convert this into malonyl-CoA first. So notice, how many carbons does malonyl-CoA have? 3. How many does acetyl-CoA have? 2. So, and we convert the 2-carbon acetyl-CoA into the 3-carbon malonyl-CoA by carboxylating it. So we add carbon dioxide. So, and there's the carboxyl group that gets added. So acetyl-CoA carboxylase is the enzyme responsible. It also involves biotin and manganese. So biotin probably being something of note in this case. Where have we seen biotin before? So biotin has been involved in other carboxylation or decarboxylation reactions as well. So here involved in other carboxylation. So, but it's malonyl-CoA that is going to be our substrate for fatty acid biosynthesis here. So one thing to note, so acetyl-CoA carboxylase, it's a multi-subunit enzyme. When the subunits aggregate, that's kind of activation. When those subunits dissociate or separate, that's inhibition. So a couple things can cause those subunits to aggregate. Those are citrate and insulin. So why would it be, why would citrate make sense to be an activator here and cause those subunits to aggregate. Why would that make sense?
Move to the side as well.
So yeah, citrate's my way of getting the acetyl-CoA out of the mitochondria into the cytosol. Also, a bunch of citrate might be like, oh yeah, hey, bye, we're out here waiting, ready to do some biosynthesis. So also inhibited, again, inhibition usually leads to the separation of subunits, and palmitoyl, I can't spell correctly, that should say palmitoyl CoA and malonyl CoA, as well as it can get phosphorylated either from hormonally through glucagon or epinephrine. These can all lead to inhibition as well. Notice, why would the presence of palmitoyl CoA or malonyl CoA, why would it make sense that those would inhibit our acetyl-CoA carboxylase? Yeah, product inhibition. So activated by a reactant, sort of, a little further up the chain than that, and then inhibited by products. Cool. So this is fatty acid synthesis. So like I said, it's not exactly the reverse of beta oxidation. Although the overall reactions look kind of like opposites, the net results, the individual details are a little more differentiation there. So if you look, we got malonyl CoA here. How many carbons does it have? 3. We just carboxylated acetyl-CoA to make this malonyl CoA. So we're then going to transfer it off to ACP. So, and notice it's still got a high energy thioester bond. So, but malonyl CoA, when bonded to ACP, that's what's actually going to get shuttled into the fatty acids biosynthesis pathway here. So we had to activate our acetyl-CoA first, and when we activated it, what do we turn it into? Malonyl CoA, but with CoA, it's not ready yet. It's got to get transferred to who? ACP. And now that malonyl is bonded to ACP, now we're good to go. Now, one thing to note, ACP and CoA are very, very similar. So they both have a high energy thioester bond. Their structures are even very similar, but fatty acid synthase is only going to recognize, so when malonyl is bonded to ACP, not CoA. Cool, so we carboxylated our acetyl-CoA. That carbon dioxide is now going to leave. So, and that's actually one of the driving forces for this reaction. It's not the most favorable thing, other than the fact that CO2 does leave, making it irreversible, and making it a little more thermodynamically favorable than it otherwise would be. So in this case, malonyl CoA is our way of still getting 2 carbons at a time into the pathway, because one of them is going to leave as carbon dioxide. The substrate it's actually going to combine with is an acetyl group to prime it. So to get going here, so all the acetyl-CoAs are going to get shuttled in through malonyls, except one. The first one has to come in as an actual acetyl group. The first 2 carbons in the growing chain actually come in a separate pathway. Acetyl-CoA turned into acetyl ACP, so also going to an ACP here. So, and that actually is then going to get transferred to the fatty acid synthase enzyme itself. And this thing is now, we say, primed. So the first 2 carbons actually don't go through malonyl CoA at all. They come from acetyl-CoA through acetyl ACP and then transferred off to the fatty acid synthase itself. That's the first 2 carbons. But all the rest of the carbons in the growing chain come from malonyl. Cool? So there's the first 2 carbons, and then I'll bring a malonyl in. Gets decarboxylated, and so these 2 carbons plus the 2 coming from malonyl give me a 4-carbon chain. Cool. Going to take that, and I'm going to reduce the beta ketone to an alcohol. That is one of the steps that looks pretty darn much like the reverse of what we saw in beta oxidation. So notice that is a reduction, so what has to simultaneously happen with that? Oxidation. One thing to note, when we're doing anabolism, so oftentimes rather than NADH or FADH2, which are often involved in catabolism, in anabolism you're typically going to see NADPH being used instead, preferentially. So the others 2 are much more common in catabolism, so, but NADPH much more common for biosynthesis for anabolism. So in this case, if we're going to reduce the ketone to an alcohol, we got to oxidize NADPH to NADP+. Cool, now that we've got an alcohol, now we're going to undergo elimination. Notice it's a dehydration step. It is also looking very similar to one of the reverse steps we saw in beta oxidation. We get a ketone, we get an alkene. So we lost, notice, how do I recognize that this is not reduction? Looks like we lost oxygen. Also lost a hydrogen. So whereas this carbon's losing the OH, the carbon next to it here, the alpha carbon's going to lose an H. Losing one of each, it is not oxidation nor reduction again. No cofactors needed whatsoever. So, and now that we have our alkene, now we can further reduce it to an alkane. This is a hydrogenation reaction. We're adding 2 hydrogens. It is therefore definitely a reduction. And if we're going to do a reduction of our substrate, then what has to accompany it? Oxidation. And for anabolism, what's our preferred cofactor? NADPH gets oxidized. Cool. This guy now is ready to combine with another malonyl CoA and repeat the whole cycle. So he then picks up 2 more carbons from malonyl CoA, goes around the chain again. Reacts with another malonyl CoA, picking up 2 more carbons, going around the chain again. And this keeps happening over and over and over and over. And if you're a mammal, when does it stop? 16. So in mammals, we stop at 16. We make palmitic acid. If we're going to make any other fatty acids, and I guarantee you contain other fatty acids besides palmitic, it's not going to happen here, though. It's going to get modified later somewhere else. So not any pathways you have to know, though.
So is that then the primer?
So correct. We only need this primer pathway right here just the first time.
I can't see
The dot, I know, it's fading on me. And unfortunately, I have no batteries. Can you see the dot at all?
Okay, yeah.
Okay. So the primer here pathway, the first one, is the only one we'd need. Then the growing chain serves as the primer to mix with the next malonyl CoA. Or malonyl ACP, I should say, rather. Cool. So we just pick up 2 carbons at a time. So if you notice, the entire process is not exactly the reverse of beta oxidation, but 3 steps look remarkably like the reverse of beta oxidation. Question?
Where is that acetyl-CoA coming in from? It's getting shuttled in?
This one right here?
Yeah, the primer reaction.
So if you look, where's this malonyl CoA coming from? Right here.
From the mitochondria.
So,
Shuttled
and where did the but what created the malonyl CoA?
in.
Acetyl-CoA. So if you notice, at first, the malonyl CoAs, all of them, we need 1 every round. And they all come from acetyl-CoA initially somewhere. But the first primer one also comes from acetyl-CoA. We're going to use 1 there. But that's only needed the first time. That's the first 2 carbons in the chain, and we don't need that ever again.
So that's just floating around with the cytosol then?
So correct.
Okay.
So notice, if you look, we shuttled some acetyl-CoA out of the mitochondria. We turned it into citrate, citrate into cytosol, and then the citrate was broken down into oxaloacetate and acetyl-CoA.
Okay.
So we got a boatload of acetyl-CoA now out in the cytosol. Some of it's turned into malonyl CoA, in fact, a great deal of it. A few molecules need to stick around to prime this thing, though.
Okay.
Cool. All right, regulation of fatty acid synthesis. You can't get out of knowing a few regulatory things, but again, at least it's not as bad as last exam, right? So a little bit of regulation here. Only 1 activator here for fatty acid synthesis, and that's insulin. Why does that make sense?
Excess of glucose you can store it in fat.
Good. So insulin's for glucose uptake when you have an excess of glucose, which means you've got lots of carbohydrate fuel. So, and notice, if I am a sprinter, let's say, and I've had some crazy workouts today, then all the glucose I take in, I'm probably just going to use, right? But let's say I'm Chad the couch potato, and I'm just taking in glucose all day long sitting on the couch. So, and my body says, he's not using it, store it. And he stores the excess glucose as fatty acids. So even if you don't eat fat, you can get fat. It's crazy, isn't it? It's kind of the whole point behind low-fat ice cream, right? It doesn't taste as good. It has extra sugar instead of fat, and that's just going to get converted into fat anyway. So what's the point? Let's eat the good stuff. So that's the only activator inhibited by. Inhibited by low NADPH, low acetyl-CoA, and low citrate. What is that pretty much an example of? So all 3 of those, well, they're all reactants needed for fatty acid biosynthesis. So if you don't have a lot of those reactants around, well, yeah, let's not have this process going because you can't do it anyways. It'd be a waste. So, and then it's inhibited by palmitoyl-CoA, again, one of the final end result products here fatty acid biosynthesis, but also inhibited by glucagon and epinephrine. So, and you'll see time and again that insulin on one side and then glucagon and epinephrine are usually antagonistic. So if insulin activates it, it makes sense that glucagon and epinephrine would go the other way.